The light from the sun hitting the lunar dust causes it to become positively charged. The charged dust then repels itself and levitates above the surface of the moon to form an atmosphere of dust. This happens due to a phenomenon known as photoelectric effect. Right from capturing those special moments in the charged coupled device of a digital camera to renewing solar energy from a solar cell, the discovery of the photoelectric effect has indeed been a boon to mankind. In the photoelectric effect, it is observed that when the light of a certain color or wavelength is incident on a metal surface, it leads to spontaneous emission of electrons. Here we will learn the physics behind the occurrence of the photoelectric effect. A path-breaking explanation of this phenomenon was given by Sir Albert Einstein in 1905, which also confirmed the particle nature of light. According to his explanation, light is emitted and absorbed as discrete particles or quanta of energy, which were later named as photons. The energy of a single photon is given by E is equal to h nu, where h is the Planck's constant and nu is the frequency of light. Einstein explained that when a photon interacts with an electron at a metal surface, it transfers its entire energy to the electron. This causes the emission of electrons and the photon ceases to exist. This phenomenon is called photoelectric emission or photoemission. But would any metal, for that matter, exhibit photoemission when some light is incident on it? Now let us study how the frequency of the incident light governs photoelectric emission. Depending on its work function phi 0, every metal surface requires a certain minimum frequency of light called its threshold frequency nu0 to exhibit photoemission. An incident light having its frequency less than threshold frequency would not exhibit photoemission. When the light of threshold frequency nu0 is incident on the metal surface, a photon-electron interaction takes place. At this frequency, the photon energy absorbed by the electron becomes sufficient enough to overcome the surface barrier and the electron just escapes from the metal surface. But since the incident photon energy is equal to the work function phi 0, the kinetic energy of the ejected electron would be 0. Next, when light having a frequency greater than nu0 is incident, the photon energy h nu is greater than the work function phi 0 of a metal. In this case, the excess energy of the photon delivered to the electron is conserved in the form of kinetic energy of the ejected electron. Mathematically, the energies sum up as h nu is equal to phi plus k, where phi is the energy required to eject an electron and k is the kinetic energy of the electron. Further, of all the electrons within the metal, the least tightly held electrons require minimum energy equal to the work function phi 0 of the metal and are ejected with maximum kinetic energy k max, while the tightly bound electrons require energy greater than phi 0 to overcome the surface barrier. Hence, tightly bound electrons are ejected with kinetic energy less than k max. The equation for maximum kinetic energy is given by k max is equal to h nu minus phi 0. This equation is known as Einstein's photoelectric equation. The frequency versus maximum kinetic energy of the ejected electron can be plotted in the graph as shown here. Now increase the frequency of incident light by lowering the wavelength. Higher energy photons are emitted from the source and hence maximum kinetic energy of electrons k max increases. Now, on increasing the intensity of incident light, more and more photons are emitted from the source and the number of photon-electron interactions increases. Thus, a higher number of electrons are emitted out of the metal surface. It should be noted that below the threshold frequency of metal, no photoelectric emission is possible even if the intensity of light increases. All these observations of the photoelectric effect explained the particle nature of light, which could not be explained by the classical wave theory. For certain metals, besides the visible light region, the photoelectric effect is also observed in the UV and IR region of the electromagnetic spectrum. Interpretation of the photoelectric effect was one of the key contributions of Einstein, for which he received the Nobel Prize in 1921. To summarize, Einstein's explanation of the photoelectric effect confirmed that light is emitted and absorbed as discrete particles or quanta of energy called photons. Photoelectric emission occurs only when the frequency of incident light is at or above the threshold frequency. On increasing the frequency of light, the maximum kinetic energy of electrons increases. On increasing the intensity of light, the photon-electron interaction increases and higher number of electrons are emitted out of the metal surface. The particle nature of radiations proved by the photoelectric effect led to the significant breakthrough in formulating a new atomic structure. Let's explore more about it in the upcoming videos.
Keep imbibing. We believe in you.